Our lesson continues looking at our stoichiometry roadmap, the mole-mole calculation, what we refer to as the heart of our stoichiometry problem. The mole-to-mole ratio, thinking want over given. I highly recommend you have out your stoichiometry roadmap. You could print one off of our Blackboard site. And when I refer to the heart of our problem, thinking about want over given, every problem we'll refer to as the stoichiometric ratio of want, coefficient of what we want, from the coefficient of what we're given. The want over given ratio moves us from one coefficient in a balanced chemical equation to the next. Let's jump in and model, often referring back to the stoichiometry roadmap. Let's review the balanced chemical equation for the production of ammonia. We wrote this together in our first video lesson. Molecular nitrogen reacts with molecular hydrogen to form molecular ammonia. The stoichiometric ratio that balanced our equation, a 1 to 3 to 2. For every 1 mole of nitrogen, 3 moles of hydrogen are required to produce 2 moles of ammonia. Stoichiometry really is nothing more than changing a coefficient and seeing what the others will do to adjust to keep the equation balanced. Suppose we'd like to know how many moles of ammonia are produced when 0.6 moles of nitrogen react with hydrogen. We call this our given quantity. We want to know ammonia from the moles of nitrogen. Now look back at our roadmap and let's get an idea of a mole-to-mole calculation. The unit given, the moles. We want to know the moles. We call this in chemistry a mole-mole calculation. And I can easily see that it's a one-step conversion, moving from moles of given to moles of what I want, where the heart of our problem is the coefficient ratio. The coefficient, what do we want to calculate from the given quantity? Now let's set that up. We want to know ammonia given 0.6 moles of N2. This is my given quantity. I like to set up my conversion parentheses so I know exactly how many steps we have to move from moles of given to moles of what we want. We want to know how many moles of NH3. This is what we call our want. What do we know about the heart of our problem, the stoichiometric ratio of want over given? We want to know the ammonia. Its coefficient is a 2. We know that every 2 moles of NH3 are made, and where's that given quantity? The nitrogen, its coefficient is a 1. 2 moles of ammonia are made for every 1 mole of nitrogen consumed. Notice what's happened? We've canceled moles of N2 and moved to moles of ammonia. 0.6 times the ratio of 2 over 1, and we would make 1.2 moles of NH3. Our first mole-mole problem. Given a mole, calculate a mole, where we use the coefficients from the balanced equation and just really a dimensional analysis. What do we want to calculate for from the given quantity? The want over given stoichiometric ratio. Let's try another. Let's write an equation of aluminum oxide from its elements, forming aluminum oxide from its elements. We want to make, so I'm going to point at it, write the equation for forming aluminum, who carries a +3, oxide, who carries a -2, so when we crisscross, we get a compound, Al2O3, aluminum oxide. Its constituent elements, the elements it's built from. elemental form of aluminum, Al. The elemental form of oxygen is diatomic, it's molecular, O2. Al plus O2 combine to form a compound, aluminum oxide's formula, Al2O3. There's our skeleton. We'll now work to balance. I noticed that I have 3 O's on the right and 2 O's on the left. I realized to get them to balance, I'm going to have to turn those both into 6's. If you started with the aluminums, we'd end up erasing, but I noticed that the odd number of oxygen on the right, I noticed that we're going to have to make them 6's, which makes this value a 4. So here's our stoichiometric ratio, a 4 to 3 to 2. Coefficients, moles, those are all known as a stoichiometric ratio. The most efficient recipe to run this equation, 4 moles of aluminum combining with 3 moles of oxygen to form 2 moles of aluminum oxide. How many moles of aluminum, this is what we want, how many moles of aluminum are needed to form 3.7 moles of our product, aluminum oxide? Our given quantity is aluminum oxide. We want to calculate for the aluminum. As always, start by writing your given quantity. 3.7 moles of our product, Al2O3, our given quantity. Now when we do that, what we're really doing is writing down this particular box. What is the moles of our given quantity? And we have a one-step conversion to get it over to moles of what we want, where we take the coefficients of want over given. I like to get my conversion parenthesis ready so I can see my target. We want to move from moles of aluminum oxide to moles of aluminum, moving from our given quantity towards the want. Notice on the Stochiometry Roadmap down at the bottom here, it's where it's telling us always move from the given quantity. So everything on the left side of your Stochiometry Roadmap represents given quantities, and we follow that pathway to calculate for what we want to know. Move from given toward the want. What about that want over given stoichiometric ratio? We want to calculate for the aluminum. Its coefficient is a 4. It's telling us from the recipe 4 moles of aluminum are required to produce 2 moles of aluminum oxide. The stoichiometric ratio, the heart of our problem, the want over given mole ratio. Notice what's happened? We've canceled the moles of aluminum oxide and have moved to moles of Al. A dimensional analysis where unit cancellation is always our goal. We would hit 3.7 times the ratio of 4 divided by 2, and I find my value when I calculated 7.4 moles of Al. Our next one reads, how many moles of oxygen are required? So this is what I want. To react completely with 14.8 moles of aluminum. Here's my given. Given a quantity of aluminum moles, calculate a mole of oxygen. As always, start with writing the given quantity, number, label, unit, 14.8 moles of Al. Here is my given quantity. I want to calculate for oxygen. I like to get my one-step conversion parenthesis ready so I can see my target. I want to move to moles of O2. So we start with a given quantity, and we calculate using the heart of our problem, the Stoichiometry Roadmap, want over given mole ratios, where moles are our balanced coefficients. Notice how we want oxygen. Its coefficient is 3. 3 moles of O2 are required. To consume completely 4 moles, the coefficient there on aluminum, 4 moles of Al. Our stoichiometric ratio of 3/4. Moles of Al canceled, and we move to moles of aluminum. Calculators, hit with me. 14.8 times the ratio of 3/4. and I find 11.1 moles of oxygen. Let's try one more mole-mole calculation. How many moles of aluminum oxide? So here's what I want to know. Moles of aluminum oxide given the quantity of oxygen moles. So here's my given. We'll start by writing 0.78 moles of O2, our given quantity in our problem. To move from moles to moles, it's a one-step conversion where we're in the heart of our problem, the want over given mole ratio. We want to move from moles of oxygen to moles of aluminum oxide. That's our product, Al2O3, the product aluminum oxide. So this is our wanted calculation from our given quantity, moles of O2. From our recipe, we need those coefficient ratios. We want Al2O3, its coefficient is a 2. So on the top goes the want, 2 moles Al2O3 from the oxygen's coefficient, which is a 3. The stoichiometric ratio of 2/3. Notice how I'm writing number, unit, label, just to be sure my units are indeed canceling. 0.78 times the ratio of 2/3, and I find 0.52 moles of aluminum oxide. We know most often coefficients stand for mole values, but when we're measuring, we don't measure in mole units. We measure by counting, we measure by weighing, we measure by taking a volume. The next example is going to illustrate what we call a mass problem. Given a mass of one of our reactants or products, given a mass, let's calculate a mass. We call a mass. Do you see how many steps are involved to move all the way from the left side of our stoichiometry roadmap to the right side? The stoichiometry roadmap consists of 3 steps. Step 1 moves us from the given quantity of grams into the mole. Now remember, it is absolutely no different from our old mole map. If we're given a mass, we know how to convert to a mole. Whatever the unit is, our job is to get it to the mole. I can count it, I can weigh it, I can take a volume, and all roads lead into the central calculation, the mole map. The same is true for the stoichiometry roadmap. If I count it, if I weigh it, if I take a volume, we want to get it to the mole. If I count, I use Avogadro's exchange. If I weigh it, I use the molar mass to exchange. And if I'm in a volume unit, I use molar volume 22.4 to exchange into the mole. Every problem involves this heart, the want over given coefficient mole ratio. So whatever unit we start with, we've got to get it into the mole. Follow our roadmap to lead to the central unit of the mole. We do our ratio, the coefficient ratios we just finished practicing. Want over given. That brings us to moles of what we want. Just as if we were looking at our old mole map, we can exchange moles to counting units, to gram units, or to volume units. That is absolutely no different from looking at the mole map, counting, weighing, taking a volume. It is absolutely the same presentation. So once I'm done calculating moles from my ratios, I just simply follow the roadmap to get the desired calculated unit. Let's jump in. A mass problem. Let's rewrite the equation for the production of ammonia. Ammonia, molecular nitrogen with molecular hydrogen, forming a group of molecule here, NH3. And we've written this several times in our lesson with a 1:3:2 stoichiometric ratio. Let's calculate the number of grams of ammonia that are produced by the reaction of 5.4 grams of hydrogen with an excess of nitrogen. Calculate the grams of ammonia. This is what we want to calculate. Given the grams of hydrogen, here's our given quantity. Now, as usual, start by writing the number, the unit, and the label of the given quantity. Where does that put us on our stoichiometry roadmap? Of course, it puts us right here, the mass of given. To move all the way from a mass of a given over here to the desired calculated unit, mass of want, we're going to need 1, 2, 3 conversion parentheses. Those 3 conversion parentheses, step 1, divide, step 2, ratio, step 3, multiply. Let's do it step by step. We've just finished writing the mass of given. I want to exchange my mass into the mole. I want to exchange my mass into the mole. I literally trip over my conversion factor, don't we? It's the molar mass of our given substance. I like to get all 3 conversion parentheses ready so I can remember my target. I know I'll have a step 1, a step 2, a step 3, where we divide, we ratio, we multiply our desired calculated quantity, grams of NH3, where the heart of our problem is the want over given stoichiometric mole ratio, those coefficients. Step 1, we want to exchange hydrogen grams into moles. Remember how we do that? A couple of visuals. If I'm at the mass scale, I want to go into the mole, I divide by molar mass. 1 mole set over the molar mass. Stoichiometry roadmap. Given the quantity, I use 1 mole of given over its molar mass of given. Given quantity is grams of hydrogen. 1 mole of hydrogen has a molar mass of 2 grams. Just the atomic weights of 2 H's added together. Grams of hydrogen have canceled and we moved into moles. Now visually, that puts us right here on our mole map. That first conversion moved me from mass to moles. Now I'm in the heart of my problem. My want over given mole ratio. Grab those coefficients from our balanced equation. We want to know ammonia. Its coefficient is a 2. The given quantity came from hydrogen. Its coefficient is a 3. The stoichiometric ratio of 2/3. Now what? We've done step 1, we've done step 2. Where we're standing now on our roadmap, we're standing right here at moles of want. I want to know ammonia grams. 1 more conversion to move me from moles out to grams. 1 mole conversion to move me from moles out to grams. Notice how we're tripping over our conversion factor. In either one of our helpful tool pages shows us that molar mass is the exchange from moles to grams. The molar mass of ammonia. I know that for every 1 mole of NH3, the formula weight of N and 3 H's added together is 17 grams. Nitrogen weighs 14. Each of the hydrogens at 1 apiece gives me the sum of 17 grams for the molar mass. We divided, we ratioed, we multiplied. The 3 steps of stoichiometry to move me from a given quantity of grams to a calculated want quantity, grams of ammonia. Now hit with me, make sure we get a common answer. 5.4 times the ratio of 1 over 2 times the ratio of 2 over 3 times the ratio of 17 over 1. And I found 30.6 grams. Let me hit again just to verify. 5.4 divide by 2 times 2/3 times 17. Yep, 30.6. Got it twice. We did our first mass problem, moving from a gram to a gram. 3 steps of stoichiometry. Let's review a balanced equation for a decomposition. We're going to decompose potassium, who carries a charge of +1, with the polyatomic ion called chlorate, ClO3 -1. Back of your periodic table is your polyatomic ion chart, the test-taking tool page provided in this course. When chlorates decompose, they release metal chlorides and oxygen gas. Elemental form of oxygen is molecular, O2. What about balancing this? 2 O's on the right with 3 on the left. I know I'm going to have to turn them both into 6's to get them to balance, making the KCl's balance with a 2 as well. So our stoichiometric ratio, 2 to 2 to 3. Let's calculate the grams of this reactant, potassium chlorate, that are necessary to produce 50 grams of potassium chloride, KCl. The given quantity is 50 grams of potassium chloride. We want to know the mass of the reactant. So here's our want, here's our given. To move all the way from the left to the right of our stoichiometry map, step 1, step 2, step 3. 3 steps to move from left to right, where we divide, we ratio, we multiply. I like to get those conversion parentheses ready just so I can remember what my target is. I want to see it at the end of my journey. My map is leading me from grams of given to grams of want, and we want to know KClO3. Step 1. Step 1, we need to move from grams to moles, just as in our old roadmap, grams to moles. The new roadmap says we still are using the same conversion. Given a mass, get it to the mole so we can set up our ratio. I don't care if we count, if we weigh, if we take a volume, our job is to get it to the mole unit. And of course we see the molar mass is our necessary conversion. We need the formula weight of KCl. Looking at my periodic table, we know potassium is 39. Chlorine, I'll say 35.5. So the sum, 74.5 grams. Now we're in the heart of our problem. What do we want to know from the given quantity? We want to calculate the grams of this reactant. Its coefficient is a 2. 2 moles of potassium chlorate are required. How about that given quantity? Its coefficient is also a 2. 2 moles of potassium chloride. The stoichiometric ratio of 2 over 2. We want over given. One more step. On our roadmap so far, we're standing here at moles of want. Here we are. One more step to get to mass. When I move from moles to mass, I trip over my conversion. I use the molar mass of the calculated substance. Just as if we were on our old mole map. We want to move from moles to mass. We multiply to head out, don't we? Using the molar mass. So we have to add a K, a Cl, and 3 O's, finding the formula weight of potassium chlorate per mole. Let's see, potassium is 39, plus 1 chlorine at 35.5, plus 16 for the oxygen, but there's 3 of them, so I multiply 16 and 3. Total formula summed is 122.5 grams. Now, let's start with our given quantity. We'll divide, we'll ratio, we'll multiply, and work towards the grams of what we want. 50 times the ratio of 1 divided by 74.5 times the ratio of 2 over 2 times the ratio of 122.5 over 1. I hit that and I found an answer, my calculated answer of 82.2 grams of potassium chlorate. Key sequence, 50 divided by 74.5 times 122.5. Since these are the same numbers, they just kind of cancel out. So the fewest keystrokes, if that's your goal. Now hit that however you're comfortable and make sure you're finding 82.2 grams. Let's work this last problem together on this page. How many grams of oxygen? So this is looking like our want. We want to calculate mass of oxygen. Are produced when we decompose 15 grams of our reactant, potassium chlorate. Our given quantity is a mass of potassium chlorate. We know to move all the way from the left to the right of our stoichiometry roadmap involves a 3-step conversion. I like to get them ready so that I can see my target. I want to move to grams of oxygen. Where the heart of our problem is the stoichiometric ratio of want over given. The heart of our problem represents the coefficients, a want over given ratio. So in our first conversion, to move from grams into moles, we've learned that it's the molar mass that's converting me. And I just found that up here. So 122.5 grams is the sum of a K, Cl, and 3 O's. Grams have canceled, and we're now standing in the heart of our problem. We want to know oxygen. See how our calculated want is oxygen? Its coefficient is a 3. The given quantity has a coefficient of a 2. Think want over given calculated quantities. So our stoichiometric ratio of 3/2. We have one more step to move out to grams of oxygen, and that's by using the molar mass, the exchange unit between moles and mass. 2 oxygens sum to give me a total weight of 32. So let's hit together, starting with 15 grams of potassium chlorate. I'm going to divide by the molar mass of 122.5. I'll then multiply by the stoichiometric ratio of 3/2 and multiply by 32, the molar mass of oxygen. And I find at the end a calculated value. I just made a mess. I found at the end here my calculated value to be 5.88 grams of O2. So in this set of problems, we have really worked at finding out how many grams of a given quantity to calculate grams of a desired quantity. The 3 steps of stoichiometry, where we divide, we ratio, we multiply. I think this might leak to the next page, so I'm going to look up here. How many moles of each product are produced when 10 grams of potassium chlorate are heated? So I'm seeing here 10 grams of potassium chlorate. And I'm asked actually for 2 problems for the price of 1. I want to get to each product. But I put this on here to represent, just think about where are we starting and where do we really need to end up. So as I think about my roadmap, I like to get my conversion parentheses ready. So let me just clean this up a little bit. So here's our calculated thing. We have a gram. See how this is a given quantity. But we want to know moles. Given a mass, calculate a mole. So think about that in terms of getting your conversion parentheses ready. Here was our given unit, the mass. We want to know moles. Not far enough over here for all 3 parentheses. So what I'm saying is this particular problem says this is a step 1, step 2, and stop. I have my desired unit after my second step on my roadmap. A step 1, step 2. So we're looking at, let me just rewrite that equation. It was on your previous page. 2 KCLs and 3 oxygen. So we can just see those coefficients readily here. Given a mass of potassium chlorate, we're going to do a step 1, a step 2, and stop, because we want to know moles of each reactant. So I'll need to do this twice. I'll need to do one for moles of KCl, and we'll need a second problem to squeeze that in there where we get to moles of oxygen. So let me give myself, sorry I keep erasing, but I'm going to end up with 2 separate journeys here. Alrighty, so given a mass of potassium chlorate, we need to use that twice, once to get to moles of KCl and once to get to moles of oxygen. Same given quantity, 2 desired calculations. So again, the same first step for both problems because we're given the same amount. 1 mole over 122.5 grams, the molar mass of potassium chlorate. But let's suppose in the heart of our problem we want KCl. Its coefficient is a 2 from the reactant who also has a coefficient of 2. The same given quantity has the same first step, doesn't it? So I'll just say that's the same first step, but now we have a different heart of the problem, because if we're wanting to calculate moles of oxygen, its calculation is 3 moles of O2 being produced for 2 moles of KClO3. So same first step, different ratios. Let me hit for the first problem. 10 grams of our reactant, potassium chlorate, divided by its molar mass of 122.5 times 2 over 2 gives me a calculated value of 0.0816, 0.0082 moles of potassium chlorate. Potassium chloride, sorry, that's the IDE over here. This is the 8. Now, 10 grams divided by 122.5 times the ratio of 3/2 to get me to the moles of oxygen, and this has a calculated value of 0.122 moles. So given a mass, calculate a mole, step 1, step 2. If we want to calculate grams starting from a mole, think about that. Starting from a mole, calculate a gram. See now what we're looking at? A step 2, step 3 on the stoichiometry roadmap. We start right in the heart of our problem, don't we? So this time, our given quantity, 2.5 moles of the reactant, which was potassium chlorate. We move to the heart of our problem, where our first desired calculation will want to calculate mass. Let's just make that potassium chloride. And I'll need some more room, and I'll give myself some more room in a moment, but let's hit for this one first. The coefficient in front of KCl is a 2. The coefficient in front of our reactant is also a 2. Excuse me. The molar mass we calculated earlier, 1K added to 1Cl, 74.5 grams. So starting at the mole places us right in the heart of our problem. We're ready for the ratio. 2.5 times that ratio of 2 over 2 times the molar mass of 74.5, and we have produced 186.25 grams of KCl. Now I don't have enough room, but perhaps you can tip your page or you have enough room in the margin. I think what I'll do to work that final problem is just give myself room here. This is not where you're to write it. I just need the extra space. Or perhaps just to lead to less confusion, I'll just extend the page and work down here. So here's the last problem, just to rewrite that out so we can see what we're looking at on our video screen. Alrighty, so I just ran out of room. We have one more problem to work. Perhaps you're writing smaller. Given 2.5 moles of the reactant, we still have to calculate mass of oxygen. I just want to complete that one. So our given quantity, again, is the mole of reactant, potassium chlorate. We begin our journey in the heart of our problem. Now I have a new desired calculated quantity. I want to know mass of the other product, the oxygen. Given a mole, calculate a mass. A mole mass problem. Step 2, Step 3 on the Stoichiometry Roadmap. The coefficient for our desired quantity to calculate here is a 3. Calculation for oxygen, 3 moles. From 2 moles of potassium chlorate. Molar mass of 32 grams per mole exchanges the mole unit into the mass unit for molecular oxygen. 2.5 moles of potassium chlorate times that ratio of 3 divided by 2 times 32 over 1, and this will show me 120 grams of oxygen. To review, to summarize, we spent time, first of all, doing some mole-mole calculations. The heart of our problem, when you see me draw that, it's referring to the mole-to-mole ratio. Those are the coefficients from our balanced equation. We then extended the borders and did mass-mass calculations, the 3 steps to move all the way from the left to the right-hand side. And in the final few examples, perhaps I give you a mass and we stop at moles, 2 steps. Perhaps I start you at moles and we want to calculate a mass, step 2, step 3 on the journey. In the next lesson, I will model other types of stoichiometry problems where we invite in particles, mass, and volume. Oh, the journeys could be endless. Given a volume, calculate the number of particles. Given the particles, calculate a mass. Given a mass, calculate a volume. Any given quantity leads me into the heart of the problem where we set up a want over given ratio and we just follow the roadmap to get the desired unit of what we're calculating for. Practice the mass-mass problems, and when you feel confident, start your next video lesson.